Dear student, myself Prof. Subbarajke. Today we learn new topic vibration produced in a string. In this topic, we can discuss a different mode of a vibration. We consider fundamental mode of vibration. Next, consider second mode of vibration, and another one we consider third mode of vibration. This mode we can consider one by one here. Firstly, we can discuss here what is the actual vibration produced in a string. See this diagram. Consider a string of length. This string of length consider small l stretched between two rigid supports. This is two rigid supports. The linear density, we consider mass per unit length of string is a small m, and tension acts on the string due to stretching. This consider capital T here. If it is made to vibrate by plucking or by using vibrator like a tuning force, a transverse wave can produce along this string. When wave reaches two fixed end, this end and this is a two fixed end, it's get reflected. Suppose this wave reflected in this way, or reflected with a change of by pi radian angle. Pi radian, the reflected wave interfere with the incident wave and stationary wave are formed, because here we consider these two waves interfere each other and they form loop. This wave is called as a stationary wave. The string vibrate with a different mode of vibration. See this diagram. This is the first mode of vibration. Next one, this is the second mode of vibration, and third one we consider here third mode of a vibration. This is a different mode of vibration of a stretching string. The string can be vibrate in a different way with a different frequency, called as mode of vibration. The string can be vibrate in a different way with a different frequency, called as mode of vibration. When string is vibrate, notes are formed at both ends of the string. This is a boundary condition. We consider first mode we call as the fundamental mode of vibration. If a string is stretched between two rigid supports and is plucked at its centers, the string is vibrate. It consists of an uh, one antinodes form at the centers, and two nodes two nodes form at its two ends with one loop form along the length. See this diagram. This is a one loop here form two nodes and one antinodes. See this diagram. Here consider two nodes from its end of the string, both end of the string, and a center point form as a antinode. This is the fundamental modes of first harmonics. The lowest frequency with which a string is vibrate is called as a fundamental frequency, and corresponding mode is called as a fundamental modes. Uh, Let small l be the length of the string, small n be the frequency for the modes, and lambda be the wavelength of the mode. Then we calculate length of the loop. We consider here length of the loop. We consider here length of loop is equal to length of vibrating string. We can consider small l is equal to lambda by 2. See this diagram. Small l is equal to lambda by 2. Then we can write here l is equal to lambda by 2. Then we can calculate wavelength. Then lambda is equal to twice l. We know that the relation between v is equal to n lambda, v is equal to n lambda. Then we can find here frequency of vibration of the string. This become n is equal to v upon lambda. Then we know that v is equal to square root of t upon m, and lambda is equal to twice l. Then this equation become n is equal to 1 upon twice l into square root of capital T upon m. Consider equation first. This is the lowest frequency with which the string can be vibrate. It is the fundamental frequency of vibration or first harmonics. Then we consider another mode of vibration. Consider as the second modes or first overtones. See this diagram. For a first overtone or second harmonics, two loops are formed in this mode of vibration. There is a node at the centers of the string and its both ends. When this string plucked at 2 point, here form a 3 nodes and 2 antinodes, here. Let small l be the length of the string. Then n1 lambda 1 be the frequency and wavelength of this mode. Then we can write length of loop. This become length of loop is equal to length of vibrating string. Then we can write here length of loop is equal to length of vibrating string. Length of loop, this become lambda 1, and length of vibrating string we consider small l. We know that another relation, frequency n1 is equal to v upon lambda 1. Consider equation second, but we know that v is equal to square root of t upon m, and lambda 1 is equal to small l. Put this equation in above equation. Then equation second become n1 is equal to square root of t upon small m upon small l. Then n1 is equal to twice into 1 upon twice l into square root of t upon m. Adjust this term. We can write this 1 upon l into square root of t upon m. Here 1 upon twice l into square root of t upon m is a fundamental frequency, then this equation we can write here: n1 is equal to twice n. N1 is equal to twice n. Thus the frequency of the first four tones or second harmonic is equal to the twice of the fundamental frequency. Twice of the fundamental frequency. And third mode we can consider here. Third mode of vibration we consider as second overtones. When string is vibrate between the two fixed point form a three loop. There are four nodes and three antinodes, then it is called third mode of vibration. See this diagram. Here consider four nodes: first, second, third and fourth, and three antinode: this. Let small l be the length of vibrating string and n2 and lambda 2 be the frequency and wavelength for this mode. Then we can write length of loop is equal to a length of vibrating string, then length of loop, this become 3 lambda 2 by 2 is equal to small l. See this diagram. This is the length of loop 3 lambda 2 by 2, and length of vibrating string is small l. Then we can write this: length of loop is equal to length of vibrating string. This become 3 lambda suffix 2 by 2 is equal to small l. Then lambda 2 is equal to twice l upon 3. We gets we know that n2 is equal to v upon lambda 2. Then n2 is equal to square root of t upon m upon twice l by 3. Then rearranging this equation we get n2 is equal to thrice into 1 upon twice l into square root of t upon m. This become 1 upon twice l into square root of t upon m is a fundamental frequency. Then we can write this equation: n2 is equal to thrice n. Consider equation 4. This equation 4 gives the second overtones of a third harmonic. This is mode of frequency thrice the fundamental frequency. We consider these three mode of vibration. First mode of vibration we consider fundamental mode. We gives frequency n. Then we calculate second mode of vibration. Then we calculate frequency n1, and next one we consider third mode of vibration or second overtones. Then frequency become n3. According to this we can write this: mode of vibration of the string gives frequency n, twice n and thrice n up to ... We conclude that straight string vibrate with all odd as well as even harmonics. That is, we can write frequency of the fifth overtones. This become p plus 1 into n. That is, we can write general formula: n suffix p is equal to p plus 1 into small n. This is general formula of a frequency of the fifth overtones. According to equation of a fundamental frequency, we consider some relation, and this relation we consider here a law of vibrating string. We know that the fundamental frequency of vibration of the stress string is given by n is equal to 1 upon twice L into square root of T upon M. This is a fundamental frequency of vibration of the stress string. Here a small L be the length of vibrating string, capital T is the tension in the string, and a small m be the mass per unit length of the string. According to this relation, we consider first law. This law is called as a law of length. Statement: law of length. The fundamental frequency of vibration of a stretched string is inversely proportional to its vibrating length if tension and mass per unit length are kept constant. The fundamental frequency of vibration of a stretched string is inversely proportional to its vibrating lengths. Here tension, mass per unit length are kept constant. That is, we can write this mathematically: n inversely proportional to small l if capital T and small m are a constant here. Then we consider second law of a vibrating string, consider as a law of tension. Statement: the fundamental frequency of a vibration of a stretched string is directly proportional to the square root of the tension if the length and mass per unit length are a constant. The fundamental frequency of vibration as a stretched string is directly proportional to the square root of the tension. Then we can write in mathematical form: small n directly proportional to the square root of capital T if small l and small m are constant. This is a law of tension. And third law of a vibrating string, consider of law of linear density, or we also call law of mass per unit length. Statement: law of linear density. Statement: the fundamental frequency of vibration of a stretched string is inversely proportional to the square root of its mass per unit length if length and tension are kept constant. We can write mathematically: n inversely proportional to the square root of m if capital T and small l are constant. We prepare some notes here. Suppose if small r is the radius and rho be the density of the material of the string, then linear density is given by, according to definition, linear density is equal to mass upon length. This equation we can write in this way: small m is equal to mass upon volume into volume upon length. Then small m is equal to mass upon volume means density. Then we can write m is equal to rho into volume, this become pi r square, and length is small l. This becomes small m is equal to rho into pi r square l upon l. L gets cancelled, remaining what? M is equal to rho pi r square. As this value we can write this: n inversely proportional to the square root of small m if capital T and small l are constant. Then we can put this value in this equation, in this relation. We gets n directly proportional to 1 upon square root of rho pi r square. Then we derive another relation, and fourth law of a vibrating string we consider law of radius. Statement of this law of radius, consider here statement: the fundamental frequency is inversely proportional to the radius of the string if density, length and tension are kept constant. Then mathematically we can write this n inversely proportional to small r if rho, L and capital T are constant. And fifth law of a law of vibrating string, this become a law of density. We can write this, the fundamental frequency is inversely proportional to the square root of density of the vibrating string if the length, tension and radius are kept constant, that is n inversely proportional to the square root of rho if L, capital T, small l, capital T and small r kept constant here. This is a fifth law considered as a law of vibrating string. Some question asked on this topic: state and explain law of vibrating string. And another one, show that the harmonics are present on the stretched string between two rigid supports. And another question, explain the vibration produced in a string when a stretch between two rigid supports. Another notes we consider here for a stationary wave set up in a string having both ends fixed, what is the ratio of a fundamental frequency to the second harmonics? We know that the relation of a fundamental frequency of vibration, we get here this fundamental frequency of vibration n is equal to 1 upon twice l into square root of capital T upon m. This is a fundamental frequency of vibration. And frequency of a second harmonic, we consider here frequency of second harmonic n1 is equal to 1 upon l into square root of T upon m. Take ratio here 1 upon small n upon n1 is equal to n is equal to 1 upon twice l into square root of T upon m. And n1, this become 1 upon l into square root of T upon m. Take ratio here 1 upon twice l into square root of T upon m upon 1 upon l into square root of T upon m. Here this gets cancelled, small gets cancelled, remaining what n n upon n1, this become 1 by 2 n upon n upon n1, this is equal to 1 upon 2. This is when for a stationary wave set up in a string having both end fixed, then the ratio of the fundamental frequency to the second harmonic, this become 1 by 2. In this way we can this point discuss this point mode of vibration of a string. In this way we complete three mode of vibration. First one is fundamental mode, another one is another mode, consider second mode, and next mode we consider here third modes, consider second harmonics. In this way we complete this point. Today we stop here. Thank you.